Hey, Noah.
Wow, this class is packed right now.
I know. Yeah, they line up to hear me talk, I'll tell you. It's really all right. I'm gonna use the restroom real quick. Do I get started? Right. So from the very beginning of the class, we were dividing up all the stuff that we do into two groups. One was descriptive statistics, and you just finished a project, hopefully finished, a project that creates this enormous um, page in your spreadsheet that creates a lot of descriptive statistics given a sample of data. You also have another sheet in your spreadsheet that allows you to do something similar with two columns of data, seeing if there's a correlation between those two things. Um, so descriptive is one of the two things that we do. We describe a sample. The other thing that we do is we try to infer what's going on with the population. And so we come back to the M&M activity that we had, where you were taking a look at the M&Ms in your hand, and we were trying to infer what the M&Ms were like inside the bag. So we spent a lot of time talking about how we describe a sample. In starting to move to what's in the bag, we're introducing a certain degree of randomness into this. Every single time I put some more M&Ms into your hand, there was a certain randomness to it as well. Would you agree? You didn't know exactly which M&Ms were going to be placed in your hand. There was a certain degree of randomness to that. And when we're dealing with randomness, we're dealing in a world of probabilities. So you might have wondered why a statistics class needs a chapter on probability. That's why. As we go from describing a sample to trying to guess about what's going on in the population, we need this language of probability to help us make that jump. And so we're going to start off here with some fairly straightforward probabilities here that I think you'll be able to discern pretty easily, as well as some terminology that allows for us to describe what's going on. So we'll just define some terms here like outcome, like event, sample space. And we'll talk about some of the things that we do to describe certain probabilities, like a tree diagram. Okay, so let's first of all start off with this here. Let me hide my face here a bit. That's much better. There we go. Um, if I toss a single coin, what's the full list of possibilities that I could get here? Yeah, so two of them, and it's true, or it's a heads or tails, right? Is that right? Okay, so heads and tails, which I'll just abbreviate with H and T. If I roll a single die, a D6, more specifically, what's the full list of possibilities? Yeah, so there's six of them. One, two, three, four, five, six. Answering a true false question. What's the list of possibilities? True and false. And tossing two coins at the same time. You've got two coins in your hands. What's the full list of possibilities here? Let's say they're two pennies. You can't tell the difference between the two of them. Two pennies. And so what's the full list of possibilities that could happen here? Ooh, heads, tails, tails, heads. What's the fourth one? Tails, tails. Yeah. If we added a third coin to this, by the way, Ta, if we had a third coin in there as well, if we tossed three pennies at the same time, we would multiply it by two. We'd have all of these with heads on that third coin. We'd have all of these again with tails on that third coin. You seemed a little unconvinced when we were coming up with this. Okay. So, but think that through in your head and see if you agree with that. Okay, so those are the list of possibilities there for all of those things. Whenever we're doing some kind of an activity that involves some degree of randomness to it, like this, we can call it a probability experiment, rolling a die, tossing a coin, okay, answering a true false question that you don't know the answer to, and just guessing at something, all right? And each one of these possibilities here we call an outcome. So we have a probability experiment and we have outcomes here. And um, we have a term for all the possible outcomes of a given probability experiment, and that's called a sample space. So you created the sample spaces for four different probability experiments just a moment ago. Okay, so we already have three vocabulary terms: probability experiment, outcome, and sample space. Okay, if we're rolling two dice, how many different possibilities are there? 36. Yeah. Now, how'd you get that? Six times six. Yeah, yeah. So that's the multiplication rule, which we'll get into just a little bit later here. But you can see the full list of ones here. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, and so on. And that's the full list of possibilities there. Now, I pulled this up here because how many of you have played cards? So some of you have not, so that's all right. That's not unusual. A deck of cards has 52 cards in it, which sounds like a strange number. They can be arranged this way in four rows of 13 cards in each row. Each one of them, there are three cards that are what we call face cards. They show royalty: king, queen, and jack. Okay, and then they have numbers that start at 10 and go all the way down here. And they end not at the number one, but at ace. And sometimes aces are regarded as really, really high, like stronger than a king. And sometimes they're regarded as really, really low, like a one. Depends on the game. But let's take a look at the four rows here. Two of them are black, two of them are red. So half the cards are red and half the cards are blue. And more explicitly, they're placed into four different what we call suits. The top one with the clover, we call that clubs. The second one with diamonds, we call that diamonds. The third one is hearts. The fourth one is spades. Okay. And actually, I'm told that this comes out of medieval culture to some extent here, describing the four different classes of people here. This is going to sound very role-playing game-ish here. You had the warriors on the bottom here, symbolized with the spade, bludgeon somebody with that. You had the clergy, which are symbolized with heart. All right. You had the merchant class, which was symbolized with diamonds. And then the last one sitting on top here, you had the common folk, which walked around with a club to, kill tonight's dinner, so to speak. So the four different classes there. And I'm told that's where it comes from, the symbolism here. Okay, so most important thing here is 52 cards, 4 suits with 13 in each suit. Let's take a look at an example here, and we'll keep this as simplistic as possible when we talk about gender. Find the sample space for the gender of children if a family has 3 children. So either boy or girl, we'll say. What are the possibilities that we have here? Well, boy, 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 girl, boy, girl, boy, boy, girl, girl. Have we exhausted all the possibilities for that involve the first child being a boy? What have we missed? Yeah, okay. So then we just repeat this same thing again here with the first child being a girl. Girl, boy, boy, girl, boy, girl, 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 boy, girl, girl, girl. All right, so we have 8 possibilities here in the sample space for having 3 kids and describing the genders of those 3 kids, assuming for none of them it's complicated. Sometimes we can place this into what's called a tree diagram to split things up a little bit here. All right, so when you have your first child, you can see how this branches out to boy or girl. And for each one of these branches, those things branch out into boy, girl, their own boy, girl for the second child here. And then each one of those branch off yet again for the third child, giving us 8 different possibilities that you can see listed on the right-hand side. So we create these tree diagrams sometimes because they help in some situations. So if we have a series of outcomes we want to focus on, namely, in this case, boy, girl, girl, that's a series of outcomes grouped together into what we call an event. This is a particular event that's taking place here. Okay, so an event is just a group of one or more outcomes put together. Does that make sense? Okay, so that's our last major foundational vocabulary term there. Okay, so we're going to do the same thing here with a coin flip. What's the probability of flipping a coin once and getting heads? 50-50. As a fraction, how would I say that? 1/2. What's the probability of flipping a coin twice and getting a head both times? That might be a little hard to think about here. So for the first coin flip, there's a 1 in 2 chance with this. I've got 4 possibilities here. How many of them show heads both times? Both times. It's just one of those 4 times, right? Here, this was a tail and then a head. This is a head, then a tail. This is a tail and a tail. There's only one of the 4 options in which we have heads both times. Does that make sense? Okay. And then let's flip the coins again. So getting a head 3 times in a row. 1/8. Yeah, there's 8 different possibilities here, and all of them have a tail somewhere in the history, except for this top one here that is heads, heads, heads. So just 1 in 8. So this again illustrates that multiplication rule that we'll talk about more in just a bit here. But yeah, those are the 3 probabilities here. And perhaps you can see that by drawing this tree diagram here, seeing the full list of possibilities and figuring out which one, yeah, figuring out which one is the one that you're looking for. Make sense? Okay. What's the probability of rolling a single die and getting a 6? Yeah, you can see that here. It's just 1 in 6. Okay. What is the probability of rolling a die, getting a 6, and then rolling the die again and getting a 6 again? Ooh, yeah. So that a lot of people say 1/12, but think that through there a bit more. How many possibilities do we have here? 36. And how many of them involve rolling a 6 both times? Just one. Good, Boozy. Okay. So all of the ones up here involve rolling something other than a 6 the first time. Um, so these down here involve rolling a 6 the first time, and only one of them involves rolling that second 6. So 1 in 36. So without using a tree diagram, what do you think would be the probability of rolling a die, getting a 6, rolling the die again, getting a 6 again, and then rolling the die a third time and getting a third 6? Ideas? Yeah, no.
72.
No, not 72. That's similar to what Ta was saying earlier, where he thought for the second one it would be 1/12. You do?
Let's say. On, I don't, hold on.
Okay. Okay. I think you got it. 144. Let me back up here for a second. What did we multiply the denominator by each time, going from here to here to here? Multiplied it by 2. So we multiplied 6 times 6 to get 36. What do you think we do next? Times 6. 36 times 6. What is that? 216. There's a 1 in 216 chance of rolling a 6, then a 6, then a 6. So about a 0.5% chance of that happening. See that? Okay. How about this one here? Now we're going to combine different ones. What's the probability of flipping a coin once and getting heads? 1/2. Okay. And then just taking a look at one of these things here, what's the probability of rolling a single die and getting a 6? 1/6. Okay. Now, what's the probability of flipping a coin once, getting heads? Okay. Rolling a single die and then getting a 6. Well, that would be this possibility here, wouldn't it? 1/12. Yeah. Now it's 1/12. So, Tom, why is that? Why is this one different than the previous one? Yeah. How do we multiply fractions again? Multiply tops, multiply bottoms. Yeah, straight across. So very, very good. So hopefully you can see that algebraically here, but you can also see it here graphically. There's only one of these 12 outcomes here that involves flipping a coin once, getting heads, and rolling the die to get a 6. Okay, so the things that we've been describing thus far are what we call classical probability. That's the stuff that, we tends to get taught in high school as well. These are the principles of classical probability. Rolling a die, getting heads or tails, pulling a card out of a deck, those kinds of things. We assume that each one of those events is equally likely. It's just as likely you'll flip a tails as you flip a heads. The coin isn't defective. Neither are the dice defective. Okay. But there are two others here. There's empirical probability and there's subjective probability. We'll get into those here as well. Let's stick with classical probability here a little bit more. What's the probability of rolling a 3 on a single die? Well, it's 1/6. But think about how you know that. How many possibilities are there when you roll a single die? How many possibilities? 6. And only one of those possibilities is a 3. So there's only one outcome in the event rolling a 3. Number of outcomes in the sample space, that's all of these things, that's 6. So 1 in 6. What's the probability of rolling an even number on a single die? Well, we still have the same number of outcomes in the sample space here. That's still 6. But there are 3 outcomes involved in the event rolling an even number. There are 3 possibilities there. So we have 3 out of 6, which I can simplify that fraction to be what? 1/2, 1/2. So when you're rolling a single die, your chances of getting an even number are 50-50. Okay, so here's the $10 equation here that we use to describe the stuff that you just did naturally. I'm going to go here. So N just means number of, just counting them all up. Number of outcomes in the event divided by the number of outcomes in the sample space. Those are the fractional things that you saw being put together each time we calculated probability. So the probability of any given event is the number of outcomes in the event divided by the number of outcomes in the sample space. So that's our formula for classical probability. And you'll be doing a number of problems like this that'll involve calculating that. Okay. Something, just a little housekeeping here. When we're describing probabilities, usually what I like to do, otherwise things become a headache really quickly, describe them, if you're describing them as a decimal, describe it with 4 decimal places unless otherwise stated, or as a percent, you can describe it with 2 decimal places here. You can see here, these two numbers are the same, decimals versus percents there. And if you have a really, really tiny number here like this that extends, more zeros out than you would have here for 4 decimal places, just round it off to the first number that's not a 0 and just describe it that way. Okay, that'll just make things easier on everybody. Cool? All right. So find the probability of getting a black 6 when one card is drawn from an ordinary deck. Well, what are the number of outcomes in the sample space? How many cards are there total? 52. Okay. How many black 6s are there? Okay, so I heard 4 and 2 here. Okay. Okay. Yeah. So there's a 6 of spades and 6 of clubs. The other 2 6s are red and not black. So yeah, it's 2 out of 52, which we can simplify to 1 in 26. 1 in 26. So when you're drawing a card out of a deck, you have approximately a 4% chance of drawing a black 6. That's at the beginning of the deck. If you're drawing from a full deck. Yeah, if you're drawing from a deck that only has 15 cards in it, then that changes it, doesn't it? Yeah. So we're assuming it's a full deck. If a family has three children, find the probability that exactly two of the three children are boys. Okay. So let's list all the outcomes in the sample space here. What did we say that there, it was boy, 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 girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, and girl, girl, girl. So how many outcomes in the sample space? There's eight of them. And so exactly two of the three children are boys. No, yes, yes, no, yes, no, no, no. So what's our answer here? Three out of eight. So three out of eight. Yeah, exactly. Two of the three children are boys. Yeah, very good. Yeah. So if you didn't have the word exactly here, then really you're finding what's the probability that there are more boys than girls, which it would make sense that that would be four out of eight or half and half, wouldn't it? 50-50 chance. It's one or the other, more boys or more girls. All right, cool. All right, so do these. I'll walk around, see how y'all are doing. These are an ordinary full deck. A king, queen, or a jack. Any of the cards that have faces. Yeah, if you need to take a look at your full list of possibilities there. Yeah. All right, what's the probability of pulling out a heart? Sounds barbaric. 13, there are 13 hearts out of a total of 52 cards. And actually, that can reduce because 13 goes into 52 four times. And so that can, one fourth, yeah, which kind of makes sense. It's one of the four rows, isn't it? Yeah. A black card. How many black cards are there? What's that? Half the deck. Yeah. So you already know it's going to be half the deck. Another way of saying it is there's 26 cards, two rows of 13 out of 52 that are going to be black here, but that will also reduce to one half. The eight of diamonds. How many eight of diamonds are there? Just one. One out of 52. Okay. How about a queen? How many queens? Four out of 52. And remember, 52 can be divided into 4 times 13. And so what does this reduce to? 1/13th. Nice. And lastly, a face card. Yeah, there are 12 face cards there. So 12 out of 52. I can break down 12 into 4 times 3. I can break 52 into 4 times 13. So that reduces to 3 out of 13. Are we all seeing that? Yeah, let me backtrack here. So just to be clear on what a face card is, it's I go even farther here so you can see the deck more. There we go. So a face card is anything that's got a face on it, like this one. So basically a king, queen, or a jack here. And so hopefully you can, I mean, one of the things that we saw over and over again here is that there are 4 rows and there are 13 in each row here. And so your probability of pulling out a 4, for example, you can say 4 out of 52, or you can just say it's one of the 13 columns here. So you can see how that would reduce to 1/13 here. If you're talking about pulling out something that's red, that's 26 out of 52, but you can also see it as being half the cards here. So you can see how that would reduce to 1/2 as well. And then lastly here, we saw this, probability of 12, one of the 12 cards that are face cards, 12 out of 52. We can also see how that would reduce to 3 out of the 13 columns. Right? So just seeing it in multiple ways. All right. We also have things called conditional probabilities, and we'll talk about these more in the next section here. Um, if I Do my chances of a parking ticket pretty much stay the same, or do they change if I park in a loading zone? They change. So my chances of a parking ticket are somewhat dependent on whether or not I park in a loading zone. Would we agree? So sometimes probabilities aren't just a single answer. Sometimes the answer is it depends. And we can describe that this way using this terminology here. The probability of this happening, given, that's what this means, given that this has happened. So that's how you read that. Make sense? We'll talk about how we calculate those in a bit here. All right, so a little bit more here. That's all classical probability. We can also calculate empirical probabilities. What does the word empirical mean? Anybody know? Yeah. Empirical, and you'll hear this word described in a number of contexts here. Empirical just means based on experience or data. You'll see that vocabulary term pop up in a lot of different situations here. I've just empirically learned to expect rain in the afternoon in northern Colorado during June. That's based on experience. So empirically, we've learned that to some extent, right? Okay, so classical probability assumes that certain outcomes are equally likely, such as the outcomes when a die is rolled or a coin is flipped or you're pulling a card out of a full deck, while empirical probability relies on actual experience to determine the likelihood of outcomes here. So here's an example. A researcher for the American Automobile Association asked 50 people who plan to travel over the Thanksgiving holiday how they will get to their destination. The results are shown in this table over here to the right. So based on what you're seeing here, it looks like 41 people are going to drive, so that's by far the most popular thing. Six people are going to fly, three are going to take the train or the bus. And it looks like if we add all those up, we get 50 people here. So, what is the probability if you tap on the shoulder of one of those people that that person is going to say that they drove? Well, that's the number of outcomes in the event divided by the number of outcomes in the sample space, 41 divided by 50. But we are picking out this probability based upon experience, right? Okay, 41 out of 50. The probability of flying is 6 out of 50, which we can reduce to this. And the probability of taking a train or a bus is 3 out of 50. Okay, so for this one here, in a sample of 50 people, 21 had type O blood, 22 had type A blood, 5 had type B blood, and 2 had type AB blood. Set up a frequency table and find the following probabilities. Basically, find the probability for each one of them. Let me ask you a question. If I were to rerun this sample again with another 50 people, do you think I'd get the exact same answers? Probably not. Yeah, so empirical probabilities sometimes can be pretty variable. They're dependent upon someone's specific experience there. All right. A recent survey found the following distribution for the number of hours a person sleeps per night. Find these probabilities for a person selected at random. Person sleeps 8 hours per night. What's that? What do you think, Ta? Person sleeps 8 hours per night. What's the probability of that? Yeah, 28 out of 100, which I might reduce to, if I cut both of those in half, what do I get? Ooh, very good. So four goes into both of these things here. And so, yeah, 7 out of 25. Seven touchdowns or four touchdowns with the extra point would be 28 points there. So, person sleeps fewer than 7 hours per night. So, fewer than 7 hours. Okay. Yeah, careful. Fewer than 7 hours per night. So, what outcomes are in that event here? Is this outcome in that event? Careful. Listen to the language. Fewer than 7 hours. Well, it's part of it. Is this outcome in that event right here? Less than 7 hours? Yeah. How about this? Is less than 6 also less than 7? Yeah. So what's that going to be?
68.
38 out of 100, right? Yeah. So, yeah, there you go. So 38 out of 100. If I snip both of those in half, I get 19 out of 50. Okay. And 19 is prime, so I can't do any more with that. Person sleeps at most 8 hours per night. So let's think about that. At most 8 hours per night. Um, so yeah, what does somebody mean when they say at most? Tomorrow I want to work at most 8 hours. From 0 to 8 hours, yeah, but not more than 8 hours. Okay. So is this in the event? Yeah, this. How about this? How about this? Yeah, so 8 hours is still okay, but at most 8 hours. Is this part of the event? No. Okay, so it's everything but this one here. So we could add up all of these, or we could take 100 minus 4, 96. So at most 8 hours would be 96 out of 100, which if we divide everything by 4, gives us 24/25. Okay, person sleeps at least 7 hours per night. Is this in the event? Yeah. Is this in the event? Okay, but we need to listen to the language here. At least 7 hours. So 7 hours or more or less? More. So 7 hours or more. So these are the three outcomes that are in that event of at least 7 hours. And what is that? 62 out of 100 or 31 out of 50? How are we doing with those? So you have to be careful. You have to think through the language that's being presented to you sometimes. Okay. Um, Empirical probabilities depend on the day, don't they? As I was taking you through that first experiment there, and I said, if we sample another people for their blood types, would we get the exact same probabilities? Yes or no? No, we wouldn't. So as we rerun these things here, um, let's take a look at the kinds of things. I actually had this simulated in Google Sheets here. So I'm rolling a die 10 times, and I got three ones, one, two, two threes, one, four, two fives, and one, six. Okay. If I roll a die, what does classical probability say that my probability is of rolling a six? 1/6, yeah, which is actually this dashed line right here. Okay, so the dashed line here is classical probability. These bars are empirical probability. Do they agree? Not really. But let's see what happens when I go from rolling the dice 10 times to 20 times. A little bit better. 30 times, 40 times, 50 times, 100 times, 200 times, 500 times. Now it's starting to kind of settle in. And here's 1,000 times. And here's 2,000 times. And 5,000 times. What are we seeing? It's increasing, but what's happening to the blue bars versus the dashed line? Yeah, they're lining up with each other. This is called the law of large numbers. Okay, and it just says that as we sample things more and 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 more than classical probabilities and empirical probabilities come together to give the same answer. Okay. We've kind of seen that here with these bars lining up very nicely with that dashed line there. So, according to the classical probability, when flipping a fair coin, the chances of heads or tails should be 50% for both. But if I flip a coin 10 times, is there a possibility I'm going to get heads every single time? Is there a possibility that that's going to happen? Yes. I think you're thinking that it's unlikely, but is it possible? It is possible. Yeah. Unlikely, but possible. Anything can happen. All right. So that would be an example where the empirical probability would be very, very different from the classical probability. If you flip it and get heads every single time, the empirical probability is 100% getting heads. Classical probability says 50-50. So the empirically determined probabilities are not necessarily the same as classically determined probabilities. However, for a large number of coin flips, these two probabilities should get closer and closer together. It would not be unusual for 4 coin flips to only get 1 head. However, it would be highly unusual to flip a coin 1,000 times and still only get heads 25% of the time. That would be very, 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 very unusual. And the more we make that number larger, 1,000, 2,000, 5,000, 10,000, the more unusual that would be. Okay. So here's some important things to keep in mind here. These are some things that that pop up sometimes, and it shows some misunderstandings the general populace has when it comes to probability. Here I've rolled a die 10 times, and I've only gotten 1 6, and I've only gotten 1 2, and I've only gotten 1 4. And so sometimes people say, well, I'm due to get a 2, a 4, or a 6 now when I roll this next one. So they'll fill things in. In classical probability, your probabilities are always the same every single time. Your chances of getting the 1, 2, 3, 4, 5, and 6 are still 1 in 6. Okay, so that's a little different. Somebody said, they usually get a hit 30% of the time. I haven't gotten a hit yet today, so I think he's due. Nope. No, there's actually no evidence for that. Okay, so that's not how that works there. Okay, here's another thing that pops up when people are working with probability. Forget how things work when it comes to large numbers of people. So let's say we've got 1,000 people here, and we ask all of them to flip a coin once. About how many of them will get heads, and about how many of them will get tails, more or less? Half and half. So 500 people of those 1,000 people will have gotten the heads, about, right? That would not be unusual, would it? Right? Talk to me. Yeah, good, okay. Now, so those first 500 people who got tails, we're going to send them home. But the 500 people who got heads, we're going to keep them, and we're going to say flip a coin again. How many of them will get a head the second time? About half again. So now we've got 250 people who have gotten heads both times. Okay, we send the other 250 people home. We ask these people to flip a coin again, and 125 of them have gotten heads 3 times in a row. Is any of this unusual? No. Okay.
I was expecting to have 1,000 people, right?
Yeah.
I was thinking they had 1,000.
There's 1,000 different people. So in that sense, there's 1,000 possibilities. But how many possibilities are there for flipping a coin?
2.
Just 2.
Oh.
Yeah, that's right. So we're now down to 125 people. We ask those people to flip a coin again, and it would be about 63 people. I mean, half of 125 is 62 and a half. So let's just make it a round number, 63. So 63 people now have gotten 4 heads in a row. Wow. 4 heads in a row. And then let's have those people flip a coin again. And it's about 32 people who have gotten 5 heads in a row. 5 heads in a row. We asked them to do it again. 16 people have now gotten 6 heads in a row. We asked them to do it again. Now 8 people have gotten 8. That's 7 heads in a row. We asked them to do it again. Now 4 people have gotten 8 heads in a row. 2 people then have gotten 9 heads in a row, more or less. And then we asked those 2 people to roll it one more time, and one person has gotten, 10 heads in a row. And they'll converge upon them, with the cameras and the. So why did you get, wow, you are so lucky. You had 10 heads in a row, and it'll be like, yeah, I was just kind of feeling like sort of this heads energy coming through my soul. And I just knew that every single time when I did this, I was going to get, a head or something like that. And they act like this is some really, really, really unusual event. Is this an unusual event? No. Given the sheer number of people that were involved with this, we would, in fact, anticipate this happening. See that? So sometimes we have a way in our culture of saying things are unusual, or dare I say magical, when in reality, if you have a good understanding of statistics, they're actually not. They're ordinary. Okay. Lastly, subjective probability here. Subjective probabilities, boy, do we see these things on ESPN all the time here. A sports writer says that there's a 70% probability that the Kansas City Chiefs will win the Super Bowl. Somebody's on, MSNBC's business segment says there's a 55% chance that we'll go into a recession next 3. I don't know what that percentage would be. Physician says there's a 30% chance that the patient will need surgery. Sometimes, by the way, that's based upon actual data, and so that's an empirical probability. But sometimes it's just based off of a gut feeling, in which case it's subjective. A seismologist forecasts an 80% chance of a major earthquake in California this century. I think that's actually about right. So those are subjective probabilities. Those are the 3 kinds. So classical, empirical, and subjective are the 3 kinds of probabilities. And we've defined what a probability is and how we calculate it using some other terms like outcome, event, sample space. And we've also defined what a conditional probability is. Let's see if we can define some of the rules that we have for probability here. You see the bottom one there is the multiplication rule. That's the one that you've already sort of figured out from having one random event followed by the next one that you multiply those probabilities out. This is actually where we start to calculate some of these probabilities a little bit more explicitly, using some equations that you'll eventually want to put into your test taking research. Okay, so mathematically, what is a probability? Can I have a probability that's negative? Yes or no? No. Can I have a probability that's 10? If it's percent. Can I have a probability that's 3 million? No. Now, what's the highest that a probability could be? 1 or in percents? What's the highest probability? 100%, right? That's what I was getting at. So yeah. So 1 or 100%. So it's a number that's somewhere in between 0 and 1. And we might describe that, using this compound inequality here that I've got. This is the way we say that something is between 2 numbers, 0 and 1 here. We might say that if something has a probability of 0, that it's impossible. If it's a little bit more than 0, we'll say that it's unlikely. The 50-50 chance would be 0.5. Likely would be getting close to 1. And if it's 1, it's going to happen for sure. Okay. What do we notice about all the probabilities for rolling a single die? For getting a 1, the probability is 1 in 6. For getting a 2, it's also 1/6. For getting a 3, it's also 1/6. If I add up all those fractions together, what do I get? 1. Yeah. So the sum of all the probabilities of all the outcomes in a sample space, I'll throw in an asterisk here, if they're mutually exclusive, those are all equal to 1. Okay. So if an event cannot occur, then the probability of that event is 0. If the event is certain, then its probability is equal to 1. So just getting you used to the nomenclature here, the notation that we use. So probability of something, we'll say P, and in parentheses, we'll put what that something is. Okay. When a single die is rolled, find the probability of getting a 9. When a single die is rolled, find the probability of getting a number less than 7, or of the probability of getting a 1, or of not getting a 1. Work on those here while I walk around. If you need to get a drink or something, or go tinkle, you can do that as well. Slide 6.
For the die, it's a regular D6. Right?
Yep, it's a regular D6. Yeah, that's important. First ones. For all of these, we're assuming a D6. Good. This one. 6, which is 1 bit. Yep. Yep. All right. Okay, so I'm seeing good numbers. Let's also get some good notation involved in here as well. So when a single die is rolled, the probability of getting a 9, well, that can't happen. So we might say 0 out of 6 or just 0 here. When a single die is rolled, find the probability of getting a number less than 7. Well, that's going to happen every single time, no matter what we roll here. So that's going to be a 1, which we might also say is 100%. When a single die is rolled, find the probability of getting a 1. For that event, that's 1 in 6, which I would say is 0.1667 or 16.67%. When a single die is rolled, find the probability of not getting a 1. Interesting. Yeah. That's 5 out of 6. And I believe that's 0.8333. Is that right?
Yeah.
Okay, so 83.33%. What do we notice about these last two probabilities? What do we notice about those last two probabilities? They add up to 100%. They add up to 1. And why is that? Yeah, so one is the probability of finding a 1. The other one is probability of finding everything but that 1. And so since everything should add up to 100%, then these two probabilities should add up to 100%. We actually have a term for this. We call these complementary events. In that one is the opposite of the other. This one right here is the same thing as before, except we just put in a very important word. The word not. Okay, so these complementary events add up to 1 or 100%. And so with that in mind, I could figure out what this is here by simply subtracting 1/6 from 1. Maybe you actually did that sort of in your head when you were coming up with this value here. Okay, so once again, if I call this probability of this event, I actually have some additional notation here. The way I say not E is by putting this bar over top of it. We just call it E bar. The probability of the complement of this event, or we might just say the probability of not E. Okay. All right, find the complement of each event. Selecting a month that has 30 days, what would that be? What's the complement of that? What's the complement of that event? Sally, what do you think? Well, 31 is part of it. What are some other possibilities? A month has 11 days? How many days in each one? Okay, for some of them. Okay, yeah, select a month that does not have 30 days. Yeah, so that's complement. What's the poem? 30 days hath December, April, June, and November. The rest have 31 except for February. So yeah. Selecting a day of the week that begins with the letter S. What's the complement? That doesn't. Rolling 2 dice and getting a number whose sum is 7. Really, I should say that this way. Rolling 2 dice and getting a sum of 7. Sum just means adding together. Derek, what do you think? Rolling 2 dice. What's that? Yeah, getting something not 7, something other than 7. Selecting a letter of the alphabet excluding Y that is a vowel. What's the complement of that? That is what? Not a vowel. Would it include Y or exclude Y? It would include Y. Since we excluded it here, we have to include it. So selecting a letter that is not a vowel, including Y. And why is it important to know what the complement of an event is? The probability of selecting a month that has 30 days and the probability of selecting a month that does not have 30 days, what should those two probabilities add up to? 1. Yeah, or 100%. Yeah. Same thing with all these other cases. Okay. So for complementary events, we have some rules here that we can work with here. So, and another way to see it is with something called a Venn diagram. Actually, it's an Euler diagram, but we'll go with this here as well. The probability of having some outcome that's in the sample space somewhere is 1. So something happening is the probability is 1. But here's the event, and the probability of the complement of that event is going to be 1 minus the probability of this event. So if this event here has a probability of 1/4, then the blue area is going to be the remaining 3/4, subtracting 1/4 from 1. Okay, so if these two colored areas add up to 1, I can find the probability of the complement of the event by subtracting the probability of the event from 1. Make sense? Just another way of seeing it. We can also write it that way or this way. Okay. In a study, it was found that 24% of people who were victims of a violent crime were aged 20 to 24. If a victim is selected at random, find the probability that the person is younger than 20 or older than 24. 30 seconds. How'd you get that? 100 minus 24. Yeah. If the probability that they're somewhere between 20 and 24 is 24%, then the probability that they're younger than 20 or older than 24, that's going to be the remaining 76%, isn't it? How are we doing with that? I'm seeing some uncertain stares here. Talk to me. Okay. So yeah. All right. So complementary events, that's our first vocabulary term here. Here's another one. Mutually exclusive events. In other words, events that don't happen at the same time. They don't hang out together. So like junior drum is, you know, that I this. So randomly selecting a female student and randomly selecting a student who is a junior. Can both of those things happen at the same time? Yeah. So these are not mutually exclusive. They're not. So think about mutually exclusive. I'm excluding you. And mutually means it's mutual from both sides excluding. That's not mutually exclusive because both can happen at the same time. Randomly selecting a person with type A blood, randomly selecting a person with type O blood. Can I have two blood types at the same time? No. So those are mutually exclusive. Rolling a die and getting an odd number, rolling a die and getting a number less than 3. Mutually exclusive, yes or no? No, because if I roll a 1, I'm satisfying both of them, aren't I? Randomly selecting a person who is under 21, and randomly selecting a person who's over 30. Those mutual, yeah. If somebody's under 21, they can't be over 30. Vice versa. Those are mutually exclusive. See the difference? See what that means? It's impossible for both to happen at the same time. So. Okay. So tell me. Think these through here. Okay, so for part A here, mutually exclusive, yes or no? Yes. If something's a face card, it can't be a 6. B, yes or no? No. So Queen of Hearts would be an example. Face card and a heart, same time. Drawing a 7 from a deck and drawing a king from a deck, yes or no? Yes, good. Lastly, drawing a queen from a deck and drawing a spade from a deck. No. Queen of spades satisfies both. Okay. So here's why this is important here. If events A and B are mutually exclusive, if either one is happening or the other one is happening, but not both at the same time, then these two events, the probabilities of these two events can just add. Okay, and we call this, creatively enough, the addition rule. Okay, so if two things are mutually exclusive, their probabilities add. So the probability of A or B happening. Notice the or here. We're going to get very, it's going to be very important that we follow this terminology here. A or B is probability of A plus probability of B here. So those things add together. Gesundheit. If they're not mutually exclusive, those things do not add in the same way that the area of A plus the area of B would not add up to the area of A and B put together because there's some overlap. See that? Yes? Talk to me. Would the area of this glob equal the area of the first circle plus the area of the second circle? Yes or no? No, because they overlap. Some things would get counted twice. Okay, so if two events are not mutually exclusive, then this rule doesn't work. In fact, we have to add another term to it, which is fun later on. Maybe coming up here pretty soon. In the United States, there are 59 different species of mammals that are endangered, 75 different species of birds that are endangered, and 68 species of fish that are endangered. If one endangered animal is selected at random, find the probability that it's either a mammal or a fish. Can something be both at the same time? No. So they are mutually exclusive. So what's the probability that something is a mammal? Out of whatever the sum is here, 75, 59, and 68, whatever that is. Somebody get that? Hmm? 207? Okay. Is that right? Let's see. So 9 plus 5 is 14, plus 8 is 22. 5 plus 2 is 7, plus 7 is 14, plus 6. Okay, it's 202. So you're close. Okay. Probability that it's a fish. What's that? 68, again, out of 202. And so the probability of it being a mammal or a fish, since they're mutually exclusive, that's probability of mammal plus probability of fish, which is equal to 59 over 202 plus 68 over 202, which is 127 over 202. Did I get that right? Okay, cool. It's about a 60% chance. Okay. So, all right. The corporate research and development centers of 3 local companies have the following numbers of employees. If a research employee is selected at random, find the probability that the employee is employed by U.S. Steel or Alcoa. We're assuming that they're mutually exclusive. In other words, nobody's moonlighting at more than one place. So what's the total here of all 3 of these? I agree, 1,110. Yeah. So the probability of U.S. Steel is 110 out of 1,110. And the probability of Alcoa is much higher, 750 out of 1,110. They are mutually exclusive. So the probability of tapping on somebody's shoulder and finding that they work at US Steel or Alcoa is equal to this plus this, which is 860 out of 1,110, which we could reduce to 86 out of 111 just by erasing a 0 top and bottom, dividing by 10. Okay. In a survey, 8% of the respondents said their favorite ice cream flavor is cookies and cream, and 6% said their favorite was mint chocolate chip. If a person is selected at random, find the probability that her or his favorite ice cream flavor is either cookies and cream or mint chocolate chip. We're assuming you cannot have more than one favorite. So these two things are mutually exclusive. So the probability of cookies and cream or mint chocolate chip is each one individually added together. So that's 8% plus 6%, 14%. Okay. All right. If they're not mutually exclusive, we mentioned that our previous addition formula doesn't work. Here's one that does work. I want you to see it this way here. If I'm trying to figure out the area of these two overlapping circles put together, so watch my pen up here. The area of A is this. The area of B is this. If I add those two things together, something's getting counted twice. What's getting counted twice? That little sliver in the middle, isn't it? So since something's getting counted twice, I've got to subtract it off. That's what this last term is here. What is this? This is the probability of A and B. That's the overlap between the two of them. So this is our general formula here for the probability of two events connected with the word or. It's the probability of A plus the probability of B minus the probability of A and B. So notice this terminology here is important, or versus and. This one always works. If two things are mutually exclusive, then tell me about what this last term is here. If two things are mutually exclusive, what's the probability that both of them are? Take a step back here. Turn off your math brain. I mean that sincerely. If two things are mutually exclusive, what's the probability that both will happen at the same time? Exactly. Zero. So for things that are mutually exclusive, this term just drops out there. That last term just drops out. Okay. A single card is drawn at random from an ordinary deck of cards. Find the probability that is either a nine or a diamond. Either a nine or a diamond. So, okay, well, probability that it's a nine or a diamond. I'm going to use my formula. It's the probability that it's a nine plus the probability that it's a diamond minus the probability that it's a nine and a diamond. What's the probability that it's a nine? No, how many nines are there in the deck? Four. Okay, so 4 out of 52. How many diamonds are there in the deck? Yeah, out of 52, how many? 13. Good. And how many cards are there that are both a nine and a diamond? One. Namely what? Nine of diamonds, exactly. Okay. Combine those three fractions together, what do we get? What's that? Ooh, you're one step ahead of me here. So 18 out of 52, which I can reduce. Let's see, would that be 9 out of 26? So I've got there. Did I get that right? It's 16 out of 52, isn't it? My bad. So it's not 9 out of 26. You said 4 out of 13, didn't you? So why didn't you challenge me? Withrow, you're wrong. All right, good job, Sally. So, let's see if I've got any more here. Let me just give you this one here. This one gets a little wordy. Eight plus three minus one. Ten. Why is that number so high? Is it because we have a lot of males or a lot of nurses? Hmm? Is it because we have a lot of males or we have a lot of nurses? A lot of nurses, yeah. We only have three males out of the 13. So yeah, it's because of the number of nurses there. Okay. That's as far as we're going to go today here, but I want to have us talk a little bit about Project 3 now. Project 3 for you is going to be your first statistical analysis. And the idea here is that you're going to choose one or more actual data sets here to take a look at. So there's a lot of different things that are available here. Heart disease mortality by state, gun mortality, labor force by country, marriage rates by states, there's divorce rates by states, there's fertility rates by states, there's drug overdose mortality by state, there's all of these things. Whichever one you choose is up to you. I would actually choose somewhere between 1 and 3, actually between 2 and 3. Because it's sometimes really cool to try and compare one to the other. Is there a correlation between growth in the arts and entertainment and growth in financial insurance? As one goes up, does another one go up as well? That kind of stuff. Here's the idea. You're actually going to write a little paper. Here's the kind of thing I'm looking for. Okay, so this is an example of one. You'll find this on MyOpenMath. An analysis of the distribution of electricity consumption among countries throughout the world. It's just a little introduction that you put in here to describe what you're going to be looking through here. Your method section is pretty strongly determined for you here. Data was obtained by. You're going to have a citation that you can take a look at here. How do you find the citation? Each data source has got this metadata file here. You just pull it up and it shows you what the citation looks like and what the reference looks like. You paste that into your bibliography at the end there.
Hold on, see that?
What's that? Yeah, there's CIA stuff in here. Yep, there's World Bank stuff. And it's not secret stuff. You can download this from the internet.
It just popped out. Oh.
Yeah. Yep. Yep. Yeah. And if you want to actually see the actual data, you can just click on the data right here and you'll see it for yourself. That's the data. So broadband subscriptions, yeah, as you might expect, the country with the most of those is China. It's 407 million of those. So they're ranked first. United States is in second place with 110 million broadband subscriptions here. And if you'll notice, I've actually got some additional fields in here referencing some other data sources here. If you want to see if there's a connection between broadband subscriptions and unemployment rate, you could make use of both of those pieces of information here. Broadband subscriptions and GDP, that's the size of the economy. Broadband subscriptions and labor force, broadband subscriptions and population. Or maybe you could check it out with all of those things there. So data was obtained from here. An analysis of the data involved some statistics kind of things here. Make sure that you reference the textbook here as well. That's our citation of the textbook here. Let me zoom in a little bit more. Okay. So notice the first thing I do when I'm taking a look at the data, what is this called? It's got quartiles in it. What's the name of it? What's this called? 5-number summary. So this gives us an initial bird's eye view of the data. So electricity consumption, interesting. Half of the countries have a value that's 6.7 or below 6.7. And yet the highest one, 5,564. So is this a symmetric distribution or is this something that's highly skewed? Yeah, so you've got a few countries that are really dominating, and you've got some of the others that are sort of off to the side here. And that gets confirmed because this is what our box plot looks like. It's like 75% of the countries are all squished into this little sliver down here, and the remaining 25% are in this one tail up here, okay? So that's what our box plot looks like, and you can talk about that. So total of 217 countries are represented by the data set, showing total energy consumption for each country. The original data showed total energy in kilowatt hours. All data was divided by 1 billion to get values in terawatt hours. The mean value among all countries was 100.328 terawatt hours, but far more representative of the data was a median of 6.798, according to Table 1. As the box plot in Figure 1 indicates, this was a highly skewed distribution with large consumption values being dominated by relatively few countries, and so on and so forth. So you can talk about that. What else can you do with your spreadsheet when you feed your data in? You could do a histogram. And again, what do we see here? Most of the countries are in this lowest category over here, and there's a few that are dominating the scene here. China, United States, India, Japan, and Russia are all dominating this here. So you can copy and and paste this into your document directly, or you can copy and paste it into a Google slide and then draw some things, draw some arrows and create some text boxes and stuff to add some things to it. And then you can copy all of that stuff into your document here as well. And then here's something that's kind of cool that you can also do with your spreadsheet. Take this first pillar over here and just blow it up so that you're looking at all of these countries that were previously just inside that first bar here. And okay, so what are some of these? Here's Germany, Canada, Brazil, South Korea, France, United Kingdom, Saudi Arabia, Italy, all of these in here. Okay. Yes, that's a possibility. This is something you can also do in Google Sheets. You can create a map that shows, in this case, the countries that have the highest amount of electricity consumption here. Okay. Notice what I'm doing here, two scatter plots. So electricity consumption, GDP, correlation, yes or no? Yeah, positive or negative? So as the GDP goes up, does the consumption go up or go down? Goes up. Same thing here with labor force. We're seeing a pretty positive correlation there as well. Okay. So you just explore these things and you should have a conclusion here that sums up what you found in a set of references in here. And by the way, I've listed this here. This is how you reference your textbook. That's Ilowski et al. 2013. And these are some examples of some of the data that you'd be working with. There's the World Bank, there's the CDC, there's the CIA, that kind of stuff there. And also, if you've found your own data set, you could also analyze that as well here. So um, you're probably wondering, how is this graded? Here's how it is graded. Let's pull up your project grading spreadsheet. And if we go to project 3 here, this is a little open-ended. So you've got what you need for full credit is 35 points. Your introduction's worth 3 points, methods are worth 2 points, and on the bottom, conclusion is worth 4 points, references are worth 1 point. And then inside your results section here, what you can do is, what I do is I just go through and take a look at all of the things that you did here. 5-number summary is displayed, okay? So you get 2 points for that. It has to also be described in the text to get full credit here. So it has to be described in the text, and that's worth 4 points. So you can't just take a bunch of graphs and put them in there. You're only going to get 2 points for each one of those things. But if you talk about them, that's worth another 4 points on all of those. Okay. And so you can put in quite a few of these. The idea here is that I want you to explore. Okay, so don't think so much about, okay, what in order to get credit, I gotta get this number of points. Because for this, 35 points is needed for full credit, but I'm allowing you to exceed that substantially. The opportunities for extra credit on Project 3 are probably the most significant of any time throughout the course. Because I really want you to take this on as something that you're not just doing for a grade, you're just doing it because you're curious. You want to find an answer to a problem. You've chosen a data set, you're taking a look at that data set by itself, as well as in concert with some other data sets here. You're doing your own exploration. All right, so 60 points possible there. That means that if you've missed Project 1 and Project 2, gotten zeros on those things, you have the potential to basically make up all of that if you get all of the possible extra credit on back, at square one, or 100%. That's square one. See what I'm saying? Yeah, no,
So, just to confirm, this will be, all the extra credit under that one will be classified as extra credit under homework.
under projects. And those points are far more powerful than homework. So that's a possible 25 points of extra credit under the projects category. So this is really a good chance for you to just play with this stuff here. So here's what I want you to do. Take a little bit of time here. I'm going to walk around to see how everybody's doing with this. Choose what data set or sets, plural, that you're going to be analyzing here. Okay. Notice some of these are by state in the United States. Some of them are worldwide by country. Okay. So take a little time on that. In fact, let's come back in about 5 minutes. Okay, so when we come back in a couple of minutes here, we're going to be pasting that data into your spreadsheet here to get you started on this. Okay. I still need more time. Find something that they want to analyze here. Okay, so let's do this. Pull up your spreadsheet. Okay, and what I want you to do is to create a new tab in your spreadsheet. And the function of this next tab here is just to store your data for this project here. So I'm going to click on this plus sign here for add sheet. And you'll see that I've created a new sheet here with this new tab down here. I'm going to double click on this name here, and I'm going to say project 3 data, or just project 3. Okay, so I'm ready to store my data into this particular sheet here, this particular page. Okay, so let me go back. Percent children underweight, under 5 by country. Anybody else doing that? Nobody's doing that one? Okay. So I'll pull this up here. And okay, so here's the data that I've got here. Now to select everything on a sheet, watch up here. To select everything on a sheet, you click on this box in the upper left-hand corner. We select all columns, we select all rows. And we'll go up to Edit and choose Copy. And then I'm going to go to my spreadsheet. I'm going to click on A1 in the upper left here, and I'm going to say Edit, Careful, Paste Special Values Only. Paste Special Values Only. And I've got my data in my spreadsheet. Okay, so you've got a copy of all the data here for this. Okay. But what are some things I can do with this here? Percent of children under 5 that are malnourished here. Well, where's my actual data here? I'm seeing names of countries, the date where the information came from, the ranking, what region of the world that this country is in. But this is where the real quantitative data is, isn't it? Would we agree? Yes? Talk to me. Yeah. And so I'm going to select all of this here. And I'm going to go edit copy. And notice I'm not going to select the column title here as well. You don't want that. That's not a piece of data, is it? But I'm going to go to my descriptive stats sheet here, click in the top cell, and I'm going to say edit. And again, it's paste special values only. And look at what I've got. I've got an average. I've got minimum, maximum, median, quartiles. Can I calculate? Can I put out a 5-number summary on this? Yes or no? Yes. I can just put out a little chart that contains all that information there. Um, I have my mean that I can list in the text there. Um, what do you think this distribution will look like? Symmetric or skewed? I'll zoom in a little here. Symmetric or skewed? Skewed. So what does that mean for countries that have a lot of children that are underweight? So half the countries of the world have a percent of children under 5 who are underweight that is lower than what percent? 7.7. Okay, so if we have the cutoff at 7.7%, half the countries in the world are less than that. Okay, but there are some that tower far above that, don't they? Yeah, so it's skewed, isn't it? So we might want to take a look at specifically what those countries are. and how that shows up here. Does this histogram help with that? It show does. Does that confirm that it's not symmetric? Oh, yeah. So it's certainly right skewed here. And so I'm curious as to what is this country? What is this country? What is these, looks like 2 countries, 3 countries, 5 countries, and so on. What are these things here? So I might actually select this and say copy. And then I don't know if you've ever done this, but you can pull up a Google slide, create a new slide. I love it. My Google Gemini voice came up on my phone. Looks like you're interested in creating a slide. So I'm going to paste this now. I don't want to link it to the spreadsheet here. I just want this to be a picture. Okay, so I'm pasting it on the slide here. By the way, before I do that, should I change what this title is here? Probably, histogram of per percentages of children under 5 that are malnourished. Put the same thing down here. But can I insert some text boxes in here? In fact, I think, sadly, that's who this is here. Okay. And so after I do all of those things here, all I have to do is select the slide in its entirety, select the slide here, Control C, and then Control V into my Google document. And I'll get this whole thing here, annotations and all. See that? Okay, so back to our spreadsheet. Relative frequency polygon, that's pretty much showing the same thing that we have here. Ogive, again, pretty much the same thing here. Ooh, box plot. Does that confirm that this is a skewed distribution? Does that look symmetric or skewed? Skewed, I agree. See that? All right. And here's what's kind of cool about this. Let's say that we want to, let's say that we want to focus in on just these top countries right in here. Okay, here's how we do that. Where's the cutoff point here? Would it be like 24.0? Something like that, would you say? Talk to me. Yeah, 24.0 all the way up to 44 or something. Here's how you do that. Notice you've got minimum in table right here and maximum in table. I can change this. I can override this. I don't have to override the maximum. That's going to be the same. But look at what it does here. We're just zooming in on these what used to be those last few columns there. So 2 countries here, 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 1, 1. So you can just take a look at those there. And if you want to turn that off, you just hit delete. Now it's looking at all the data. See that? So maybe the minimum should be 20. That might be a little more healthy there. So, okay. So yeah, if you want to zoom in on the data, you can do that as well. Let's see if I can compare this with something. Okay, so here's my data here for this, and here's, oh, should I compare it to population, labor force, GDP, or unemployment rate? You decide. Which one? GDP. Okay. So I need to get these two columns sitting next to each other here. So let me just Control C and Control V over here. And then this is GDP, Control C, Control V right here. So I've got GDP on the left as my X values, and I've got percent of children malnourished on the other column here is my Ys. So now I'm going to select two columns of data. And where am I going to go? I'm going to copy it. Where am I going to paste it? Not descriptive stats, regression. I've got two columns right in here. So I click on A1, and again, this is going to be paste special values only. Huh. Well, that's interesting. Boy, that's a weird piece of data there. That might be an outlier. So I might actually just get rid of that. See if that changes the data at all. Oh, it's not the only one. I was wrong. Let's put it back. Undo, undo. So yeah, a little crazy. Do we see uh, a good correlation here? I don't see one. Yeah, not at all. Okay. And by the way, this isn't the right title, is it? Got to change that up there. Okay, so that one, and by the way, that's an important finding. Is it an important finding to find that there isn't a correlation? Yes or no? Yeah, okay. So I can go back and try some other ones here as well. And I'll get 6 points for each one of these correlations these scatter plots that I plot and I talk about. Okay. So I could take a look at unemployment rate. Seems like unemployment rate might have a really strong correlation with hungry children. Okay, so what else was I going to do here? So you can see the different kinds of things you can do here. Histograms, box plots, 5-number summaries, bar graphs, maps, scatter plots, mean standard deviation, interquartile range, somewhere in the text. That'll give you a point. All right. So explore, enjoy. Yes. Yeah. Still regression. Yeah. So you'll have a scatter plot that you can put into your document here. So have fun playing with this. You think here, what else can I throw at you? Oh, yes. Um, here's how you cite the textbook citation and reference. So that's in here inside Project 3. It's an example Project 3 report. Is a tutorial that can talk to you a little bit about how to do this, go over some of the stuff I went over through today. Here's all the data. And let me see here. I kind of want to push this to the 26th here. So I think I will do that. So Project 3 turn in. That'll be nice. Thank you. That'll be right here. So we'll have that due Thursday night, the 26th here. All right. So just be doing analyses for the time being here and see what you come up with. And then from there, you can write your introduction and your conclusion. From that point out, methods and stuff are pretty much set in stone. And then we'll talk about that more as we come together next time here. Yeah, so you've got two homeworks that are due Thursday night, homework 3.1 and homework 3.2 and 3.3. All right. Anything else for the good of the order? Okay. Have a good day, everybody.